This one we're talking about derivatives. So, I hope you know what a definition of a derivative is because I ask you this very often. So, in case you forgot, which I'm sure you didn't, definition of a derivative is, here, let me write this. There are a few. Okay, the first foremost one that you should think of, and you should know by heart, is a derivative is the slope of the tangent line at a point. So, what this means is you have your graph and you have your function. Ooh, ugly. A tangent line is a line that only touches the graph at one particular point. So if I wanted to know what the tangent line to this point was, let's call that A, then it would look like, let me see how well I can draw this. It would look like that. Close enough to that. And I know it's like touching here, but theoretically it only touches at that one point A. So that is what a tangent line is. And a derivative is telling you what slope this tangent line is, what slope it has. So that's why it's at a point, because it's when you take a derivative, you do it at this specific point. So you take the derivative of the function and then you plug in an a to find the slope at right here at a. So in your head, when you want to think about derivatives of a oh, that's better. Even though it's technically not touching this red part, but that's fine. You just think in your head like following the curve of the graph. So like the tangent lines over here, you see they first decrease, but then they start increasing here, decreasing, and then you draw there, you draw there. See how it's like touching points along this curve, and then the slope starts increasing as you fall along there. Okay, so that's how you can think of it conceptually. Another way that your math problems might say derivative is instantaneous rate of change. This instantaneous rate of change, this means derivatives, so they just say it in using 4 more words, I guess. So that's just saying the rate of change at this specific point A. And it's the same thing as the slope. So these all mean the exact same thing. Okay, these derivative and slope and instantaneous rate of change, it's all the same thing. And then you have your limit definitions. These, sorry, not that, just this. These also mean derivative. So you want to be able to look at those things and think that's what a derivative is, and they want me to find the derivative. So if a question asks you, like, what is the slope of a tangent line at this point, you're going to be like, okay, what I need to do is take the derivative of the function and then plug in the x value at that point to find the tangent line at that point. Or if they ask you, what is the instantaneous rate of change of blah blah blah, then you know you're taking the derivative of blah blah blah. Okay. And then something that we want to clarify is the difference between average and instantaneous rate of change. Average versus instant. So the average rate of change is the slope that you know. it's the slope that you learned in like 5th grade, which is y2 minus y1 over x2 minus x1. So average rate of change is rate of change over an interval. So if you have your graph, and it looks like this. Why do I always draw my graphs like that? I'm going to change it up. Okay, that's pretty much the same. How about that? Sure. Then your average rate of change would be from like here to here. It's a rate of change over an interval. So this point could be like x1, y1, and this point could be x2, y2. And the slope is the slope of the line in between them. So this line right here. And that's average because it's over this period of distance. But instantaneous, it's only at one point. So instantaneous for the same graph, it would just be at one point right there. What's the slope of this line? So that's distance. So this would be, if this was like called A, point A, instantaneous rate of change at point A would be the slope of this line. I'll just keep that there. Let me condense this. Okay. So don't want to get these mixed up. Okay. It's the average rate of change is pretty much it's like the limit definitions of the derivative without the limit part. So like this and this. You see how this second one right here, it looks oddly like f of b minus f of a over b minus a. Well, that's because it literally is that. So that's how you find yeah, if you only want to memorize the limit parts, you can find average rate of change just by chopping off that limit part, and then yeah. So that's just a way to remember how to find average rate of change. But also, I feel like everyone knows this, so don't worry about that too much. Okay. Let's talk about derivative rules. Zoom in here. I'm going to move this to the side. So these are important. They're how you take derivatives. Okay. So the first one that you need to know is power rule. This is probably the one that we use the most often, and it's you just moving the exponent of some function in front of it. Here, I'll write just like, let's say this is our function, equals 5x to 7th. That's our function. Now, if we wanted to take the derivative of this, all you do is you move the exponent into the front. So you're multiplying it to the x now. And then you decrease this exponent by 1. And when we move it to the front, there's already a 5 there, so that means our 7 is going to multiply to this 5. So it looks like 5 times 7x to the 6. Because remember, between there and there, you minus 1. Yeah. And then 5 times 7 is 35, so it's really just 35x to 6. That's power rule. And then chain rule. Chain rules, a lot of people get confused about, because it looks like there's a lot going on. So if I write something like chain rule, you know you have a case of chain rule when you have two functions like inside of each other, essentially. So a lot of times conceptually, they'll write it like f of g of x, and they'll be like, find the derivative of h prime, find the value of h prime of 3, something like that. And then what you have to do is you have to first take the derivative of h. So the way you do chain rule is you take the derivative of the outside without touching the inside. So all I did was add a little prime, right? Take the derivative of the outside. And then you take the derivative of the inside. So, oops, that's just g prime. And then if they wanted h prime of like 3, you just plug in a 3 wherever you have a x. So now it's g prime, f prime of g of 3, and then g prime of 3. But for our specific example here, first you take the derivative of the outside. So you want to pretend this inside is just like one entity. It all moves together. So we have a exponent here, so when we take the derivative, we know we're going to use power rule. So bring that to the front. Keep the inside intact as one thing, because remember, we're pretending it's one entity right now. And then decrease the exponent by 1. So it's very similar to what we did here. Oops. And then you can chain rule the inside, which means you take the derivative of the inside. So the inside is, derivative is 3x squared plus 2. So this would be the derivative of this right here. So remember, at first, keep it all together, and then you can take the derivative of the inside. That's chain rule. And, okay. And then we have quotient rule. So, write h. Oh, sorry, you have to write f prime, because these two are not equal to each other. Yeah, it's okay. I'll just use, like, I'll write it with some general functions. So, quotient rule. Oh, you know what? I should probably just do product rule first, because then quotient rule is easier to memorize. So for quotient rule, you have some function times some other function. So this could look like, if I had like an actual example, maybe 3x times like wait, I'm thinking. Oh, 3x times like cosine x. Yeah. So this is a function and this is a function. And they're separate functions because you can't combine them in any way that would make them like one thing. So this is function, this is function. And essentially all you're doing is you're flipping which one you take the derivative of at a time. So first we take the derivative of the first one, which is f, and you just leave g alone. And then you take the derivative of g, and you leave f alone. That's the product rule. So if this is our f, and this is our g, you have f prime. So take the derivative of the first one, aka f, it's just 3, and then you leave g alone. Add Okay, you're adding for product rule. Take the derivative of g, which is negative sign, and then you just leave f alone. Okay, squeeze it in right there. So now if I wanted to clean this up, normally you put the constant in the front, and it's a negative, so I'm going to write minus 3 sine x. So this would be your derivative of this. Okay, I'll leave that there. And then we have quotient rules, so this line. Okay. So I'm going to do both a general and then a specific example again. So this time you're still doing that alternating of which one you're taking the derivative, but instead of getting added together, like in product rule, you're going to subtract them. And then you're going to put it over this bottom function squared. So it's going to look like derivative of the first one, leave the second one alone, minus derivative of the second one, leave the first one alone, and everything over the denominator squared. Okay? So if we had an example, let's say we had x cubed over tangent x, then the derivative would be the derivative of the first one. This is like what I'm calling the first one. Derivative of f. And then this is g. So it's f prime g, g prime f, okay? So f prime g minus g prime f. Oh, sorry, that's not f. Remember, the derivative of tangent is secant squared, okay? This is a trig derivative that you should memorize. And everything over g squared, so tangent squared. And that's your derivative. Although I would probably move this one into the front just so you don't confuse it as part of the argument here. Yeah, why don't I do that just to clean it up? So that is your derivative. So let's quote, those are the derivative rules. And yeah, okay. Let's go over some specific derivatives that you should know. Okay, I'm just gonna write sine, cosine, tangent out. But really, you should know these already. Sine, derivative sine, derivative cosine, and derivative of tangent. I feel like I did this already, but I don't remember, so I'm just writing it again. And then so a bit more obscure, but you should still know, is the cosine, cosecant, cosine, and cotangent. So derivative of secant is secant tangent, and derivative of cotangent is cosecant squared. And then all the ones that say co are negative, okay? So that's just one more tip to help you memorize these derivatives. And then you should also know how to take the derivative of e. And I'm writing a u up here because I want you to memorize the universal version. So this can work for like anything that's in that u. So the derivative of e is always going to be whatever that thing is first, and then you chain rule it, so du dx. So the reason I say this and I don't just put an x there is because then this part would just be dx, which is just 1. So it's just very limited essentially, because derivative of e to the x is just e to the x. But then you wouldn't know how to do the derivative of like e to the negative x squared, because you just know it as it's the same thing. So why don't we do e to the negative x squared actually? So if our function was e to the negative x squared, then what we do is, for our derivative, this is u. So anything, the entire exponent of e is u. And you just keep it the same for now. And then you chain rule the u, so the derivative of that, which is negative 2x. So this is the derivative of e to the negative x squared. Okay, so e is a very simple one. And then you should also remember derivative of natural log of u. And again, I'm writing u because, wow, my n's and u's look the same. Okay. Derivative of natural log is u prime over u. Okay? So if it was just an x, this u prime is like du dx. So if it was just an x, it would be like dx dx, which is also just 1. So again, not very all-encompassing, so that's why I'm showing you the version with u's. So let's say we had natural log of 3x plus 5. And then f prime would be u prime over u. So the derivative, if this is u, it would be the derivative of this over this. So the derivative of this is 3. And then just over that argument. So that's the derivative of natural log. Okay? So these are probably the ones down here, like these ones are the ones that you want to remember. These ones, they're important to know, but not as important as these. Okay. So let's talk about implicit differentiation. So implicit differentiation is just doing derivatives, but with both x's and y's. So generally, when we take a derivative, you see how all of these, we just wrote f as f prime, but in implicit differentiation, we're actually involving that f in our derivative. So should I just make one up? Okay, well, I'm not looking for it, so. So it's kind of similar to how we separate variables when we want to solve some whatever question. Oh, but that's like the opposite of implicit differentiation. Okay, so generally, the question is going to ask you to like find dy dx. And they give you y equaling, or no, they give you like, something like that, equaling a number. It's something like that. It's just an example. So you see how the y's are integrated into our function? So we're going to take the derivative of this entire thing. And everything is with respect to x. So when you take the derivative of y, it's going to become dy dx. Because if you just make it disappear like you normally would, that means it was a dy dy derivative. But we're not taking it with respect to y, we're taking it with respect to x. So whenever you take the derivative of y with implicit differentiation, you have to write dy dx after all the y's you take the derivative of. So I'll just show you. Oh wait, I forgot about this red mark. Dang it. So let's take the derivative of this. So x is easy, it just becomes 1. Now this, you see how this is a function and then this is a different function? So they're like two different variables. So we're going to have to do product rule. And this 2, I'm just going to keep it attached to that x. So if I name this one like f, and then this one's g, here, I'll just write f, g. Remember, product rule is f prime g plus g prime f. Okay, so f prime, aka derivative of f, is just 2. And then g plus g prime, which is dy dx, because its derivative of y is just 1, but it's with respect to x, so you have to add on a dy dx. So, and then g prime f, so 2x. Okay. And then we just have this one to take the derivative of, which we can just use power rule. So take the exponent down and then subtract 1. I'm just going to write y. And then again, we need to remember to write our dy dx. So remember, the reason we have this is because we're taking the derivative of y with respect to x. So it's kind of like a chain rule. It is a chain rule. And the derivative of 3 is 0. Don't forget to take the derivative of that 3, because if you don't, it's how a lot of people miss easy points. So now what we want to do, they're asking us to find dy dx. So we're going to separate these from the rest of the function. So what we want to do is move everything that doesn't have a dy dx into the other side. So this 1, this 2x, they're all going over there. So we have our dy dx times 2x. And then I'm going to write this dy dx first, just for organization. And then we subtract 1 to the other side, and we subtract a 2y to the other side. So negative 1 minus 2y. So now what we can do is both of our terms have a factor of dy dx, so we can factor out a dy dx. And then the inside is just left with 2x minus 2y. And then we're just going to divide this 2x minus 2y into the other side. So now we're left with dy dx on this side. And then this is our answer. That's what dy dx is. And sometimes they'll ask, like, they'll give you values of y and x, and then you just plug them in there. Sometimes they'll only give you x, and they want you to find y. So if you only give an x, how do you find what y is? Well, you just go back up here into your original equation. You just plug in your x, and then you isolate y to get y by itself, and then it'll show you literally y equals whatever value you got after plugging in x. Okay? So that's implicit differentiation. Let's move this over. Okay, I'm gonna stop this one right here, and then we can go over more advanced derivative problems.